All right, honor chem students. The last lesson we had, we were talking about kinetic energy, which was the energy of motion and having a change in temperature using the MCAT equation. Today we're going to use a different type of energy, or learn about a different type of energy calculation in terms of chemistry, and that would be potential energy. And we often call this the energy of a phase change because that is where energy is being supplied when you're heating something out. And let's say you're melting an ice cube like you guys were doing in the first activities that we had you guys do. There was some energy being supplied into that, into the ice cubes in order to make that melt. So there are some key words to know about here when we're talking about energy of a phase change. And you know these words because you've probably known them since elementary school. You can go between a solid and a liquid, and we call that melting, right? And you can go between a liquid and a gas, and we would call that boiling. Okay, you could also consider it evaporation, but that's a bit of a different phenomena that I want to we'll talk a little bit more when we talk about vapor pressure, which will be in the next unit. So right now I'm talking about like a melting point, like going between a solid and a liquid, and the temperature at which a liquid would boil. That would be called a boiling point that goes between the liquid and the gas. You can also do the reverse of this, where you would be going from a gas to a liquid, and that's called condensing. And you can also go between a liquid and a solid, and that is called freezing. So that would be the freezing point. So these are all key words for potential energy. When you hear them, they sound like you're going through a phase change. Going this way, so going between a solid and a liquid, you are increasing potential energy. And what you're really doing is you're spreading apart the intermolecular forces between the solid and the liquid. So going this way, it's all about increasing potential energy, and going this way, it's decreasing potential energy. And when we're talking about this, I'm just going to kind of draw this. I'm going to draw this a little bit lower here. So I'm going to extend the page here a bit, and I'm just going to draw a water molecule. So you can kind of think about what we're talking about if we're talking about freezing water or solid water, what we know of, versus liquid water. So if we think of solid water, we know that water actually would hydrogen bond. And in that hydrogen bond, if we have 100% hydrogen bonding and it's all in that nice array, then you'll notice here this would be what we call the IMF, and in this case it's a hydrogen bond. What breaks during a phase change? Do you break this bond right here between the oxygen and the hydrogen, or do you break the bond, the IMF, the intermolecular force between the two water molecules? Pause for a minute, think about that, then get back to me. Okay, hopefully you're thinking it's this right here that will break. And that indeed is what happens during a phase change. The energy is going into breaking an intermolecular force, going from a solid to a liquid. Okay, we know that because we know in a phase change, it's a reversible process. You can go between solid and liquid, and you can go between a liquid right up here and a solid. So they're reversible. So that means you're not changing the substance, the unique characteristics of that water molecule. Okay, so it's a little bit on phase change things there. Okay, so what we have here then is on page 3 of your thermal packet that hopefully you guys had printed out. There is a table of what we call the molar heat of phase change. And this has a whole bunch of stuff here. It's got the compounds that we're going to be using in our worksheet for the day. So that is all here. And you will notice that there is a table that says melting freezing point. And so think about that. The melting point, if you're going from a solid to a liquid, actually happens at the same temperature that would be its freezing point, going from a liquid back to a solid. So these numbers are the same. It's just a matter of which phase you are going between. Are you increasing your potential energy? If you are, then you're calling it a melting point. If you're decreasing your potential energy, you're calling it a freezing point. But the interesting piece here is we're going to look at ethanol, for instance, and here's the molecular formula for ethanol. And if you were looking at this temperature, or this freezing melting point, which happens to be at negative 9.7 degrees C, this is what we call the molar heat of melting. It also has another name, and I'm going to kind of give you guys, let's see if I can get my pen to work correctly. This also can be called the delta H of fusion. So I'm going to just put FUS there. Fusion is what that stands for, the delta H of fusion. So I'm going to write fusion down here. That's what that column is, the delta H of fusion. And that is the amount of energy. So it would take 8.30 kilojoules, notice that unit is in kilojoules, for every mole of ethanol to melt. So each substance has its own unique delta H of melting or delta H of fusion. Same thing for boiling. Each substance, as you know, has its own unique boiling point, and that's what I have here. Again, it can be a boiling point or a condensing point. And also, there is something called the delta H of vaporization, or the molar heat of vaporization, and we represent that as delta H of vaporization. So it's delta H of vape, okay? And this would be the amount of energy it would take, 40.4 kilojoules per mole, to get 1 mole of ethanol all into a vapor phase, okay? So one of the last things I want to talk about, which is one that we use a lot here, is water. We know that water freezes, and it would take 6.0 kilojoules of energy in order to freeze that water. And that is a relatively low number compared to 40.7 kilojoules of energy to go from a liquid water to get steam. So look at the difference of those two numbers and think about, why is this number so high relatively compared to these numbers here? So stop and think about that for a minute. Hit pause if you have to. Okay, why would this number be so high compared to a delta H of fusion? Well, it makes sense to me because in water you have to break every single hydrogen bond in order to get steam. So remember, in a gas, there is no IMFs. So there are no intermolecular forces. So you have to break every intermolecular force that liquid water would have, and that's why it takes so much energy. It's also the reason why steam burns actually are more dangerous, and they can be more damaging on the cellular level than just even getting burned with hot water. So something to think about. I'm going to pause right there. The next video that we're going to have is we're going to talk about how to do calculations with the molar heat of phase change. So look for that next.